Chapter 12, Optical Communications, Part 1, Refraction. So this is the background for the Optical Communications or Fiber Optics chapter. And first thing we need to remember is that the speed of light varies depending on the medium. But it is always obeys the wave equation, that the speed of light in the medium is equal to the frequency multiplied by the wavelength. Make sure you got this labeled on your data sheet. So in a vacuum, C is equal to 3 times 10 to the 8 meters per second, and that's a fact you have to memorize. But in most mediums, it will be lower than this because they are more dense, so things travel more slowly. And here we go, we've got a couple of examples. So 3 times 10 to the 8 meters per second for a vacuum, whereas diamond, which is more dense, is only 1.24 times 10 to the 8 meters per second. This brings us on to our next idea, the refractive index of a medium. This is equal to the speed of light in a vacuum divided by the speed of light in the particular medium, and this gives us a measure of density. So in other words, if something is very dense, that means that the speed of light is very low, and if we decrease the speed of light, that must mean that we are increasing the refractive index, hence why I'm saying it can act as a measure of density. This is an equation that's not on your data sheet and underlies a lot of what we do in fiber optics, so do make sure you've made a note on it. Okay, so let's have a look at a couple of questions. Let's say we're asked to calculate the refractive index of a diamond, and we're given the speed. So we can use the equation that n, the refractive index is often given the letter n, is the speed of light in vacuum divided by speed of light in the material. So this is 3 times 10 to the 8 divided by 1.224 times 10 to the 8. So that's 2.42, rounding to 3 significant figures. There are no units for the refractive index. Second question, we're told an optical fiber has a refractive index of 1.5. Calculate the wave speed in the material. So we just rearrange this equation, swap over n and speed of light. So the speed of light in the material will be equal to 3 times 10 to the 8 divided by 1.5. So that's 2 times 10 to the 8 meters per second. So make sure you're confident using those, as we'll come back to using these ideas later. Okay, let's talk about refraction. So this is something that you'll have covered in GCSE physics, but kind of a reminder here. When crossing from one medium to another medium, light bends. And you see this effect when you look at sticks in ponds and things like that. Going into a more dense medium, it bends away from the boundary towards what's called the normal. Going into a less dense medium, it bends towards the boundary, so away from the normal. And at a critical angle, all of the light bends back into the medium. So let's have a look at this. So on this first diagram, there is a little bit of light being reflected at the boundary, but most of it's going through, it's being refracted through, and if I just continue that line, it would be going up here, but it's bending back towards the boundary. And this is fast, or in other words, this is less dense. And this is more dense. That's why it's going slower. And the critical angle, so-called because it's the very first point, when none of the light escapes the material. So when we're talking about the angle, we actually measure it from the normal. So if you imagine a line going down, that's the angle we normally talk about. And that will, of course, be getting bigger, and once you get big enough, then you've got the critical angle, and no light escapes. And if you go just a tiny bit further, and just the tiniest of tiny bits further, then we got what's called total internal reflection, where all of the light bounces back inside our material. Now, just note, this only occurs when going from more dense to less dense, because if we go the other way, then it doesn't work at all. So if this is our light, and we're going from, if we go the other way, just to be really clear why it doesn't work, it will bend towards that normal. So if that was the line that it wants to carry on, it will bend towards the normal, so away from the boundary. So you can't get total internal reflection unless you're going more to less dense. Both materials are transparent in this case because we're looking at fiber optics, but the light is totally internally reflected at the boundary. And this is how fiber optics work. Please make sure you got this diagram drawn. It is a tricky diagram to draw, I admit, but it does explain all the different parts. So the core is where the light is bouncing along in the middle. It's very, very thin. The cladding is the layer of material just on top of it, and we choose this cladding to help us choose the critical angle, and so we pick cladding with particular properties to make that critical angle easy to access, and so we don't have any light being lost or dispersed outside of the cable. And then we've got a bit of coating, and then the jacket is mechanical strength. So this is what happens. The light goes along, and at each boundary it totally internally reflects. So it goes all the way through. Do make sure that you've got both of these diagrams, particularly the second one, paying close attention to detail on that. There are two types of fiber optics. There is the single mode, and this is much narrower, and it only allows one path of light down the core. This is particularly suitable for distance transmission. And we also have the multi-mode, and this has a much fatter core, meaning that we can have more paths of light going through. It is cheaper to manufacture, but it does suffer from more dispersion. 12.2 covers dispersion, so I'm not going to go into detail on that now. The main thing is you need to understand that's 9 micrometers, that's 62.5. This is an example. These aren't values you have to memorize, but you do need to understand the difference between a single and multi-mode. So why do we bother with fiber optics? Why is fiber optics taking over all of our internet connections? Well, you need to be able to list 3 advantages and 3 disadvantages, but please do write them all down so you've got a clear understanding of what's going on. So advantages. And the first advantage, the big one really, is that the bandwidth is much, much higher than copper cable. There are other good reasons, but really the big one is that the bandwidth is much higher. A much higher width of frequencies, which means a lot more information can be passed down, and more channels can be put in there when we talk about time division multiplexing. Another big advantage is that it's immune to electromagnetic interference. This kind of ties in with the second one in a minute. So the way that what we're doing is we're sending pulses of light. Light isn't charged. Light has no charge at all, which means that if there's any stray signals from another cable next to it, another copper cable, or there's a lightning strike, or I don't know, an electric eel if it's on the seabed, whatever it is, these will not interfere with our signal because it's not got charged electrons flowing. It's just light particles. Also, because it is not electromagnetic, that means there is not an electromagnetic field, so it's really difficult to tap. It is possible, but you pretty much have to cut open the cable, put in a device to measure the signal, and then keep it transmitting with a transmitter as well. And only that way would you be able to hack it and not let the people know. If you just cut into it and started measuring, people would realize very quickly and just stop transmitting. Whereas normal cables do actually have an electromagnetic field that kind of flows around them, which you can measure without disturbing the information flow. And we don't really need to go into the detail of the electromagnetic fields, but we need to be aware of them. This is the distinct advantage of fiber optics. Power loss, there are dispersion, there are ways that we lose power, but they are much lower than copper cables. The signal strength, the power stays higher for much longer, much lower attenuation. And there is a physical advantage that they are much thinner. So if you're trying to lay cables in a particularly narrow area, you can have much thinner cables. So it saves space, which also saves cost in terms of digging. There are two main disadvantages. You need to know them both. They are a lot more fragile than copper cables. So if you bend them far enough, they break. They are glass, after all. And they are much more modern technology. So at the moment, they're much more difficult to install and a lot more expensive. But that doesn't make them impossible. And I'm sure with time, that difference in cost will decrease rapidly. Okay, so we need to be aware of the fiber optic transmission block diagram. It goes through a transmitter into a multiplexer, goes through some fiber, uses a regenerator, demultiplexer, receiver, and then out. And that's all you kind of need to be aware of. So do make sure you sketch this diagram. But that's it. We will go in the last part of this chapter into the detail about the transmitter and receiver circuits. So we will cover them in 12.3. So we will cover those circuits, very basic versions, and actually they're fairly simple circuits. This is just kind of affirming it's just pulses going down a cable, pulses of light. And the amplifier that we use can be optical to electrical to optical. So we might take the optical signal, convert it to electrical, amplify it, convert it back to optical, or we do have things that can amplify entirely optically. Multiplexing. So we talked about multiplexing. There are three types: time division, frequency division, and wavelength division multiplexing. We already know about time division multiplexing. I would recommend that you do a quick sketch of these diagrams, but it should be something that you're quite comfortable with. Frequency division multiplexing, again, is something that we've already seen. So time division, yeah, it's just a little bit of thing, and we do the time frames and all the normal stuff. So signal 1, signal 2, etc. And frequency division means that we split them into different frequencies. But wavelength division multiplexing also means we're splitting them into different frequencies, essentially because C is equal to F lambda and C is constant. So if we change the wavelength, let's say we increase it, then we've got to decrease the frequency to keep this constant. So this is really just a little bit of definitions you need to be aware of. When we talk about frequency division multiplexing in optical communications, we are talking about analog signals modulating the carrier, so there's pulse of light. Whereas when we talk about